All right, so far, Wes, I think the only thing you missed was I was reminding folks that if you're going to submit a rewrite problem. Okay. All right, so should we get started? Are there questions from last time? First, let's do that. Are there questions? No. Okay. Well then, the assignment, by the way, that's due Thursday covers just up through logs. There's nothing on today's material that's covered on that assignment. So we're going to talk about relations today, and a relation is basically a function, not a function, a correspondence between elements of two sets. So it's sort of like you could take a function and relax the requirement that each input can map only to one output. That's something that's special that makes something an actual function. With a relation, you could have, really, it's anything goes. So we're going to do some examples. And first, we'll start with just recalling the definition of the Cartesian product of two sets. So if I have a couple of sets, A and B, the Cartesian product, A cross B, is just the set of ordered pairs where the first coordinate comes from A and the second coordinate comes from B. The order matters, right? When you say A cross B, that's different than B cross A. So if A is the set 1, 2, 3, and B is the set 2, 4, A cross B, their Cartesian product is a set whose elements are ordered pairs. So as long as the first element comes from A and the second element comes from B. So 1, 2 is in there, and 1, 4 is in there. So that's if my first coordinate is 1. Then I can do the same thing for the first coordinate of 2 or the first coordinate of 3. So 2, 2, 2, 4, 3, 2, 3, 4. A relation from A to B is really just any subset of the Cartesian product. So that's what I mean when I say like anything goes. Like you don't need, there's no special restrictions like we have on something to make a relation a function. Every function is a relation, right? With an added requirement that each element of A can only correspond to one element of B. But with the relation, anything goes. So we usually use capital letters to denote a relation, but sometimes we find there is conventional to use symbols like the little squiggle or the triple equal sign. So there we have the Cartesian product of A and B up there. Let's find some relations from A to B. Let's say R1. A relation is just a subset of this Cartesian product. So like for example, maybe I pick 1, 4, 2, 2, 3, 2, 3, 4. I just picked some elements from the set. There's a relation. Just a little bit of a note on notation, I guess. If we take a look, I'm just picking the element, the ordered pair 3, 2, arbitrarily. So we say that 3, 2, that ordered pair, is an element of the relation R1. We might also say, this is the same as saying 3 is related to 2, so I'd say 3 R1, 2 is another way of saying that the ordered pair 3, 2 is in the relation R1, which is the same as saying, just in words, 3 is related to 2. What's another relation? Just another relation from A to B.
1, 4, 2, 2, 3, 4, 3, 2.
Oh yeah, yep. certainly that's a relation. Any subset of this Cartesian product, right, is a relation. In fact, this relation, 1, 4, 2, 2, 3, 4, this relation is also a function. So R2 is a function, and R1 is not. Can anybody point out why I know that?
Because there's no shared first.
There's no shared first coordinate, yeah. Like 1 goes to 4. What's that?
So like on active, it's 1, 2, 3. On another one, it's 1, 2, 3, 3.
Yeah, and it's not that, like, if I made another relation that was just 1, 4, 3, 4, that would also be a function. I don't need everything in A to have to be a first coordinate. What makes the top one, what makes R1 not a function, is I've got a repeated first coordinate. Like 3 goes to 2 and 3 also goes to 4. That's not allowed in order, if I wanted a function. It's totally allowed for a relation. I could also, I mean, this is perhaps less interesting, I could take the whole Cartesian product itself. Everything's related to everything. Like, that's a relation, you know? So, that's what makes something a relation, and the inverse relation always exists. So, on the next page, the inverse relation is actually, if I have a relation that I've defined by just taking ordered pairs like we did, the inverse relation is really easy to get. You just reverse those ordered pairs. And the inverse relation is a relation from B to A. So in the previous example on R1, we had 1, 4, 2, 2, 3, 2, 3, 4. This, the inverse relation, which we denote with the superscript -1, just like we did with the inverse functions. We're just going to reverse each of these ordered pairs. So 4, 1, 2, 2, 2, 3, 4, 3. So R1, that first relation, that's a subset of A cross B, and its inverse is a subset of B cross A. So we've been talking about like a relation from A to B. When you see the words a relation on A, that always means a relation from A to itself. So it's a subset of A cross A. And then it can be convenient to use matrix notation to denote a relation. So suppose we have a couple of sets. A consists of the elements alpha, beta, gamma, and B consists of the integers 1, 2, 3, and we're defining the relation by that ordered pair. So with matrix notation, what we do is we index the rows by the domain elements, and we index the columns by the codomain elements. And here's what I mean by that. I'm going to have, so the domain here is alpha, beta, gamma, so I'm going to have 3 rows. I'm going to have an alpha row, a beta row, and a gamma row. That's what we mean when we say index the rows by the domain elements. And we're going to index the columns by the codomain elements. That means I'm going to have a 1 column, a 2 column, and a 3 column. So I have a 3 by 3 matrix. To write the matrix that represents this relation, I look at those ordered pairs. Notice that alpha is related to 1, right? There's our first ordered pair. So that means in the alpha 1 position, I'm going to put a 1. Notice that alpha is not related to 2. Alpha 2 is not in the relation, so I'm going to put a 0 there. And alpha is related to 3, so I put a 1 there. So the matrix that represents a relation consists only of 0s and 1s, and it gets a 1 if the element A is related to B in that position. Otherwise, it gets a 0. What does the second row look like?
0, 0, 1.
0, 0, 1. And how about the last
1,
one?
1, 0, 1, 1, 0.
1, 1, 0. Great.
So was this named, I mean, if this is just a grid,
Mm-hmm.
was this named the Matrix notation before the Matrix movies or after the Matrix?
The matrix as an array of numbers has existed for centuries, so yeah. All right, pretty fun. This is like a gentle introduction to a relation. Basically, just decide what you want related to what. Now we're going to look at more interesting relations, right? Relations in general, maybe not so exciting, but relations can have certain properties. So a relation is said to be reflexive if, let's see, if A is related to A for all elements in your set A. And here we are specifically looking at, we're saying let R be a relation on A. So we're talking about a relation from a set to itself. And such a relation is reflexive if every element is related to itself. That's what the first one says. A relation is symmetric if whenever you have A, B in the relation, you must have B, A. So you have symmetry. And it is anti-symmetric if there is no symmetry ever. Like, a relation being symmetric means whenever you have the relation going in one direction, you have to have it going, you have to have all instances of symmetry. Like, if you have a bunch of symmetry, but there's an ordered pair where its reverse is not in there, then the relation itself is not symmetric. A relation is anti-symmetric if there are no instances of symmetry at all. Like, if you have, and here's how we say suppose you had an instance of symmetry, what we think of as an instance of symmetry. I could say, oh look, here's A, B is in the relation R, and now B, A is in the relation R. If you suppose that you have an instance of symmetry, then it turns out that in fact they were just the same element. It was actually just an example of the relation of an element being related to itself. And then transitive. A relation is transitive if whenever you have A related to B and B related to C, then A is related to C. Sort of like a leapfrog property. So we, in the last section, defined some relations just by explicitly listing ordered pairs. A lot of the time, interesting relations are going to be ones where we're working with a set and we just define the relation by describing what it means for two things to be related. Like here, we're defining the relation less than or equal to on the real numbers by saying A is related to B if and only if A is less than or equal to B. So the usual meaning of that symbol. We're going to see which properties this relation has. And it's on the real numbers. So first, let's check, is it reflexive? If I pick like an arbitrary real number A, is A related to itself under this definition of the relation?
Yes.
Yeah, why?
I can't say.
Okay,
Everything's related to itself
why?
because of
So we're checking to see, is it reflexive? I've heard two people say yes, and I agree, but we need to be able to say why. It's really a one-liner. Like, it's not like a big argument that we're going to need to make here.
That's the way it is.
Well,
That's pretty neat.
that is definitely a one-liner, but it doesn't really explain it.
Is that all elements of A are
Okay, I'll write this part of the proof. Okay, yes, because for any real number A is less than or equal to itself. right? Certainly because A is equal to A. Sometimes if I'm given a new relation, right, one of the things I might do is just play around with elements and see what's related to what. Like an example is not an argument, but it can help me understand what the relation is. So this relation is defined by saying A is related to B if A is less than or equal to B. So 3 is related to 5. -7 is related to -1, right? 0 is related to any positive integer. It's just the regular. So any real number is going to be related to itself because it satisfies the or equal to part. How about symmetric? Symmetric is the one that says if A is related to B, then you must have B related to A. So come up with an example of, so Ali says no. I agree with Ali. Can we come up with an example of two real numbers that are related? Like there's literally countless to pick from. 3 is related to 4, right? Great. So Ali says that this is not symmetric, and I agree, and we're going to use 3 and 4 to illustrate. We're going to make a counterexample. Three is less than or equal to 4, right? So 3 is related to 4. Can we reverse that? No, it's not true if I reverse the order. And that's it. That's all we need. Note that a counterexample, an example is never a proof by itself, but a counterexample is always a proof that something's not true, right? So how about, is it anti-symmetric? I heard no. Can we come up, if it's no, can we come up with a counterexample?
4 and 4. Wait. This is the same one as the one above. 3.
Well, so anti-symmetric is the property that says there is no symmetry ever. Like I can never reverse the order unless it's just an element being related to itself. So what do you think?
Yes.
Okay. You say yes. Ali says yes. I agree. And now we need to write something that works for all real numbers, right? So we can't just use an example. Although an example can be a great way for us to get started thinking about it. If we think it's anti-symmetric, the way we're going to do this is just consider if A is less than or equal to B and B is less than or equal to A, then, well, again, this is really a one-liner. There's not a whole lot. These are just real numbers. They're numbers on the number line. If A is less than or equal to B and B is less than or equal to A, then the only way that can happen is if A and B are the same number. So it is anti-symmetric. What about transitive? So Ali says yes. What would it mean to be transitive? Maybe we should scroll up. So Ali says yes and gives an example.
I would say yes.
Okay, so we're saying yes, and here's the example that Ali says. He says 1 less than or equal to 2, and 2 less than or equal to 3, and certainly 1 is less than or equal to 3. There's an example of an instance of transitivity. That, as an example, doesn't stand alone, but I think it certainly can help shape our thinking and how we want to write this out. What we write has to be valid for all, like any triplet of real numbers. So we need to let, for any real numbers a, b, and c. Suppose, or if we have a less than or equal to b and b less than or equal to c, then again, this is just the real number line. We have to have a is less than or equal to c. Just because that's how less than or equal to works. Okay, so there's a relation, right? We just described what it means for two real numbers to be related. We saw that it's reflexive, anti-symmetric, and transitive. It's important to note, like people think it's important to note that a relation could have some of these properties, could have none of these properties. A relation can't be symmetric and anti-symmetric at the same time, but it doesn't have to be one or the other, like one or the other. It's possible for it to be neither symmetric nor anti-symmetric. Okay, here's a fun one. We're defining a relation that we're calling squiggle on the integers by saying that a is related to b if and only if a minus b is even. So if I subtract and I get an even number, then they're related. We're going to check to see which of these properties it has. So let's start with reflexive again. So we're trying to see is every integer related to itself? That's the question that we're trying to answer. And in order to answer that question, every time I get a new relation, I have to kind of train my brain to think in terms of that relation. Every time I check a property, I have to go back, okay, how is this relation defined? So the way this relation is defined requires me to look at the difference, a minus b, and to see if it's even. So I'm checking to see, is a related to a for every integer a? In order to answer that,
Wait, I'm sorry, what is this squiggle?
it's what we're calling this relation. So it says define the relation squiggle. Like instead of calling it less than or equal to, instead of calling it big R or big S, like we did in the last section at the beginning of class. So what we have to check out now, if I want to know if A is related to itself, I have to look at the difference A minus A, which is 0. You know what's true about 0? Well, what? It's even, right? It is a multiple of 2.
I've had people argue that against me. It's always a long
You feel like what?
I've had people say that it's not.
0 is even. 0 is a multiple of every integer. 0 is even. 0 is a multiple of 2. It's a multiple of 3. It's a multiple of 4. It's a multiple of 5. It's a multiple of everything. No, because it isn't. It is not odd. It's a multiple of 2. It's not one more than a multiple of 2.
It's odd in that it's peculiar.
Okay, I'll give you that. So here we know that A is A minus A is even. So that means that A is related to A. This gets a big yes. All right, symmetric. So for symmetry, we want to know if I have the relation going in one direction, can I reverse it? Like if A is related to B, does that force B to be related to A? So let's think of some integers that are related. Can give it a minute, try to think through and give me a pair of integers that are not equal, that are not the same. And tell me, like, let's try to find a pair that are related. That are.
And by related, you mean A minus B, right? Is even. 5 and 15?
5 and 15. So 5 and 15, yeah, because 5 minus 15 is negative 10. That's even, right? Can we reverse it?
minus 5 is 10.
Mm-hmm.
It's also even.
So what I'm doing now when we think about this is to try to develop a hunch. So when we think about the relation going the other way, we just reverse the order of subtraction, right? Do we think that'll affect whether or not the difference is even or not?
No.
No. What happens when you reverse the order of subtraction?
Because it's going to be true in every case where they're either both even or both odd. So
Right,
if they're
but
both, it's going to be true in either case. So
right. So when you reverse the order of subtraction, what is the effect on the difference?
it just turns negative.
Yeah, right, changes the sign. Okay, so that sounds like we think it's symmetric. Now we just have to write the argument. It won't take very long, but we have to go back to how this relation is defined. So let's suppose A is related to B. We want to answer the question, is B related to A? So since A is related to B, that means that A minus B is even, right? Or a multiple of 2. So I'll say it's 2 times K for some integer K. In order to answer is B related to A, we have to look at the difference B minus A. So B minus A, you said, we've already observed, it just changes the sign, makes it negative or whatever. So I'm going to just use that. B minus A is the negative of A minus B. What's A minus B equal to? So I got negative 2K. And now I'm just going to drive it home. I'm going to like just cross every T and dot every I. This is 2 times negative K. I've written it as 2 times an integer. That's even. So B is related to A. This gets a yes.
Are we allowed to use the fact that it's symmetric as a way to say it's not?
Yeah, good. So I don't know if Ali heard it, but the question was, can we use the fact that it's symmetric to show that it's not anti-symmetric? Yeah, a relation's not going to be both. So if we showed that it's symmetric, then we can just cite that as a reason that it's not anti-symmetric. You could also just give an instance of symmetry, like as a counterexample. I think Wes said that it was, you said 5 and 15.
Mm-hmm.
So like 5 is related to 15, and 15 is related to 5. But certainly 5 is not equal to 15. Okay, one more. The last one is checking to see if it's transitive. This one probably takes like the most writing, but it's not terrible. And I should probably leave a little bit more space because I write kind of big these days. But is it transitive? So I'm going to go back to the list of properties here, and I'm just going to note paying special attention to the reflexive, symmetric, and transitive. Reflexive says everything's related to itself, so I just need to have an argument about one element of the set. Symmetric says if I have a relation of A is related to B, then B must be related to A, so that requires me to have pick two arbitrary elements of the set. With transitive, I need 3 elements, right? A, B, and C. And maybe we could play around and see if we can't find an instance of transitivity. So 3 integers, A, B, and C, where A minus B is even, and B minus C is even, and also A minus C is even. In fact, let's start by using the 2 integers that Wesley picked before, 5 and 15. Can we pick a third integer that like 15 is related to?
30.
30? 30 minus 15 is 15, which is not even.
45.
45, okay. So 5 minus 15 is negative 10. 15 minus 45 is negative 30. And 5 minus 45 is negative 40. All of those are even, right? So there's an instance of transitivity. 5 related to 15, 15 to 45, so 5 is related to 45. All right, so let's see if we can't write out this argument. Let's suppose A is related to B and B is related to C. We want to answer the question, is A related to C? So if A is related to B, that means that A minus B is a multiple of 2, right? 2 times K. And B is related to C means that B minus C is also a multiple of 2. Now I can't use K again because it's not necessarily the same multiple of 2, but let's say 2 times J, where K and J are integers. What is it that we want to look at to determine if A is related to C?
If A minus C.
Mm-hmm. So we're going to do some algebra. And I'm going to use one of the oldest tricks in mathematics. I'm going to add 0 to that expression, which we're totally allowed to do, right? Doesn't change it. I'm going to add 0 in the form of subtracting B and then adding B. And I'm doing that because now I can kind of group it. I can look at it with this under this grouping. We know what A minus B is. That's equal to 2K. We know that B minus C is equal to 2J. And what are we going to do next? We're going to take a 2 out of it, yeah. And K plus J is an integer. So that means that A is in fact related to C, so the relation is transitive. When you're working with a relation, I do encourage you to kind of play around with examples. Try to get a feel for what the relation does. Use examples to help you develop a hunch about whether or not you think the relation has a property. If you're using examples and you deduce that it doesn't have a certain property, that means that you've found a counterexample, and that's all you need to do is say, it doesn't have the property, look at this counterexample. If you're playing around with examples and you think it does have that property, then you just say, okay, now how do I write this, an argument that applies to all elements of the set and not just the ones that I've used. Questions? Okay. An equivalence relation is a relation that is reflexive, symmetric, and transitive. So let's look back at what we just did here. This relation that we were just working with, we showed was reflexive, symmetric, and transitive. So yeah, it's an equivalence relation on the integers. For equivalence relations in particular, sometimes you'll see the little triple equals sign used as a symbol instead of a squiggle or a capital R or something. The one that we just worked with, saying, A is related to B if A minus B is a multiple of 2, is a certain class of equivalence relation, a certain type of equivalence relation that we're actually going to work with more in chapters 5 and 6. Saying that A minus B is divisible by 2 means that if they're related, it means that they're equivalent mod 2. And you might have used the mod function in some of your coding courses, but it's pretty big in number theory. We're going to see more of it in chapters 5 and 6. So we're gonna work with another similar relation. We're gonna say we've got this relation equivalence mod 3, and we're saying that A is related to B if and only if A minus B is divisible by 3. Same kind of relation. Let's run through this. It shouldn't take us too long because the arguments that we're going to make are really similar to the ones we made before, to the ones we made in the last example. So is this reflexive? What do you think? And why? What's the question we want to answer when we ask if it's reflexive? What does it mean to be reflexive? Ali says yes, it's reflexive. Why? You don't have a reason?
Not a reason I'm confident.
Okay. Okay. Ali says because A minus A is 0. Yeah, look, every time we're working with a relation, we go back to how it's defined, right? So this says A is related to B if A minus B is divisible by 3. So if is A related to itself, well, let's let A be an integer and observe. A minus A is equal to 0, which is divisible by 3, right? This is a multiple of 3. 0 is equal to 3 times 0. So A is related to itself. So this gets a yes. In this example, I just want to, the last one we did when we looked at the relation where we said A minus B, or A is related to B if A minus B is even, the way they worded that question is, which of the properties does it have, right? So we checked all 4. This one, they're saying, is this an equivalence relation? So we only have to check the 3, right? I'm not going to bother writing anything about anti-symmetry because we just need to check to see if it's reflexive, symmetric, and transitive. So for symmetry, we need 2 elements. Let's let A and B be integers. And suppose that A is related to B. We want to answer the question, does this force B to be related to A? What do we think? Ali says yes.
I was going to say, what does Ali think?
I mean, so again, this relation's defined by looking at the difference, right? A minus B. And when we think about reversing the relation, we'll just look at the difference B minus A. What effect on the difference does it make when you reverse the order of subtraction? Makes it negative, changes the sign. Does that change whether or not the number is divisible by 3? No. So our same argument will work. So we think the answer to this question is yes. So let's say since A is related to B, then A minus B is a multiple of 3's, 3 times K for some integer K. What do we want to look at?
Look at for
Mm-hmm. And how can I write that B minus A? Right, so it's a negative of a minus b, which is minus 3k, or 3 times negative k. So yeah, b is related to a. This gets a yes. And now transitive. How many elements do we need to grab to talk about transitivity? 3. So let's let a, b, and c be integers. And what do we do? What do we suppose?
That A minus B is divisible by 3 and that B minus C.
Mm-hmm. Yep, I'm gonna first just write it this way, but that's exactly what we're gonna where we're gonna go from there. So A is related to B, and B is related to C. So that gets us, right, A minus B has to be some multiple of 3, and B minus C is a multiple of 3. Can't be the same multiple of 3, so maybe I'll call it 3J, or you could call it whatever, use whatever letter you want, where K and J are integers. What do we want to look at? Like, the question we're trying to answer is A related to C? Yeah. We can just recreate that argument. So this is A minus B plus B minus C. Kind of group the terms in that way. This is 3K. Yeah, 3K plus 3J. What are we going to do next? Take the 3 out. And K and J are integers, so K plus J is an integer. Pretty exciting. What does this allow us to conclude? Yeah. So yes, it's transitive, and that means that it's an equivalence relation. So, having shown that this is reflexive, symmetric, and transitive, we conclude that this is an equivalence relation on the integers. How we doing? Sam's doing pretty good. I'm just filling Ollie in because he wasn't here to see that. You cracked your back crazy. You're still alive. That's good.
It was like 5 each time you did it.
Yeah.
Yeah, it's pretty bad.
Mm-hmm.
Yeah.
Oh, no. Okay. So,
Pretty cracky individual.
so let's, we're just going to kind of sketch out the argument. We don't have to like write the full, complete arguments for this part, only because I think right now we have an idea of how it's going to go. Let's let M be any positive integer, and we're going to define a relation. We'll call it equivalence mod M on the integers by saying that A is related to B if and only if A minus B is divisible by M. It's the same kind of relation that we did in the last two examples, right? In the first one, we said, oh, their difference is divisible by 2. In the second one that we did, we said, oh, their difference must be divisible by 3. As it turns out, there's nothing special about what kind of integer we have to pick there. As long as we fix one, here we're calling it M, and say, see if their difference is divisible by M. So for reflexive, again, I'm not gonna bother writing the nice nicely worded proofs because this is the third one we're doing, and I think we all kind of get it. But what do we look at to demonstrate that this is reflexive? Yeah. Mm-hmm. So, yeah. Like 0 is a multiple of m. So this gets a yes. Is it symmetric? We got a yes or a ye. And so let's say if A is related to B, then that means A minus B is a multiple of M. So that means B minus A is just going to be what? Negative MK. Or K times negative M. Or M times negative K. There we go. So yeah, that means that B minus A is a multiple of M. So B is related to A. That gets a yes. Transitive. We grab three integers, right? We need the integers A, B, and C. We suppose A is, oops, not 3, is related to B. And B is related to C. That gets us some equations, right? A minus B is M times K, and B minus C is M times J. So A minus B is, what do we get?
So A minus C.
Oh, A minus C, thank you. So for, yeah, so we have MK plus MJ, and then we factor. At this point, the arguments just seem like, oh, of course it is. Like, they're exactly the same. There's nothing special about which number we pick, as long as we fix an integer and say, oh, the A and B are related if their difference is divisible by whatever. That's equivalence mod M. Now, here's something that is kind of interesting when we have equivalence classes. Let me just finish this up. A is related to C. This gets a yes. This is not the only kind of, I mean, we've focused on this type of equivalence relation. There's other types of equivalence relations. There's other equivalence relations. You might see some on the next assignment that you do. But this type will show up again and again for us and be a pretty important one. When you have an equivalence relation, one thing that is interesting to do is to look at the equivalence classes. So here's what we do when we find an equivalence class. First thing we do is we fix an element of your set. So we were just looking at relations on the integers, right? Equivalence relations on the integers. So I might fix an integer like 0 and say, what are all the other integers that are related to 0? And we call that the equivalence class of 0. So let's do that for the equivalence mod 3 one that we did on the last page. Let's start with, might as well start with 0. We call this capital E sub 0 for that equivalence class. So these are all, we're going to be all the integers divisible, all the integers that are related to 0. So all, let's see, A in the integers such that A minus 0 is a multiple of 3. If A minus 0 is a multiple of 3, that means A is a multiple of 3. The equivalence class of 0 is going to be the easiest one. The others are not hard. But this set is going to consist entirely of just all multiples of 3. So there's infinitely many. And I'll use as odd numbers, not necessarily odd numbers. It'll have some odd numbers and won't have all of them. It will have some even numbers. It's going to be all the multiples of 3. So like -9, -6, -3, 0, 3, 6, 9, etc. It's an infinite set, right? Subset of the integers. So notice that 1 is not in that set. So let's see what's related to 1. So these are going to be all the integers, every integer a, such that a minus 1 is a multiple of 3. Now I'm gonna rewrite this, do a little algebra. This is, I could just get a by itself. A is equal to 3k plus 1. And writing it that way is kind of helpful because I can think of everything in this set is going to be precisely 1 more than a multiple of 3. So it's easier to kind of come up with the elements. We just wrote down the equivalence class of 0 was all multiples of 3. This equivalence class is going to be everything that's 1 more than a multiple of 3, so I'm just going to add 1 to each of those elements. So -8, -5, -2, 1, 4, 7, 10. Note that 2 is not in either of these two equivalence classes. So let's see what's related to 2. The equivalence class of 2, if you're related to 2, that means that a minus 2 is a multiple of 3. And if we do a little algebra to rewrite this, that means that a is 3k plus 2. So 2 more than a multiple of 3, or 1 more than the numbers in the set right above it. Negative, what do we get? -7, -4, -1, 2, 5, 8, 11. So all of these are infinite sets. What about the equivalence class of 3? It's going to be back to what?
It's going to be back to the first one, like everything's equal to 1, but it doesn't matter.
Right, yeah, it's going to consist of precisely the same elements. Yeah. Yeah, because look, if something's equivalent to 3, right, that means that a minus 3 is a multiple of 3. Or a is 3 more than a multiple of 3. And if you're 3 more than a multiple of 3, you're a multiple of 3, right?
Are you though?
I'm pretty sure. I've studied this extensively.
I haven't done that.
And I'm pretty sure that if you add 3 to a multiple of 3, you get another multiple of 3. What do you think is going to happen when we get the equivalence class of 4? It's going to go back to the equivalence class of 1. So this relation is reflexive, right? So we're not surprised that 0 is in the equivalence class of 0. 0 had better be equivalent to itself. 1 had better be equivalent to itself. 2 had better be equivalent to itself. One important thing to notice about these sets that we just wrote down, there's 2 important things to notice actually. Every integer is in one of these sets. All infinitely many, right? In fact, we can count them. We got 0, 1, 2, whoops. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, we can just count them, right? They go in order. And I can count them going the other way. Right? All the integers are represented. Also, none of these 3 sets overlap at all. They are all disjoint. So I've got a set, I've got a set of sets, right, these equivalence classes, that account for all integers and that don't overlap at all. And in mathematics, we call such a group of sets a partition. So the equivalence classes of an equivalence, the equivalence classes of an equivalence relation always partition your set. That means that every element of your set A will belong to precisely one equivalence class. So all your elements are accounted for, and there's no overlapping at all. Here's a simple example. We're going to define the equivalence relation. I'm not going to ask you to show that it's an equivalence relation, although you could. It would take maybe 2 or 3 seconds. We're going to define the equivalence relation equals on the real numbers by our usual interpretation of what it means to say A equals B, right? A and B are related if and only if they're equal, if they're the same number. What are the equivalence classes of this relation? So think about it this way. 0 is a real number, right? I hope so.
Even number.
Yes. What's related to 0?
Everything.
0.
Anything else? Not a trick question. No. Because look, we're saying that this is, we're defining this equivalence relation just by equals. We're saying A is equivalent to B if A is equal to B, right? So this just consists of the single element 0. No other real number is equal to 0. So like there's nothing else we can include.
So
There's an infinite number of equivalence classes. So that means that for any real number A, the equivalence class of A is just the set consisting of that single element. There are infinitely many equivalence classes.
That's a long way of saying A is a real number.
Well, that A is a real number?
That A is a number. Just,
Well, no, not really. I mean, that A is the only real number equal to itself.
Yeah.
Yeah. Yep. So there are infinitely many equivalence classes.
But any number can work.
A is equivalent to itself forever.
Yeah, and it's equivalent to itself and only itself. So there are infinitely many equivalence classes that just consist of that single number. So infinitely many equivalence classes that are finite sets. Contrast that with what we found here, where we had a finite number, 3 equivalence classes, that were each consisted of infinitely many integers.
And the difference is just the action we're doing.
The difference is what?
There's just the action we're doing on elements, because in this one we're using equals and the other one we're using not 3 or something.
Yeah, so what you describe as the action that we're doing, it's just how we define it, like what we have to check, right? Like we had in the mod equivalence relation, we just had to do the subtraction and check to see if it's divisible by 3. Here, this is pretty simple. And is anybody else relieved that equals is an equivalence relation? Seems like that should be the case.
Pretty nice.
Yeah. Questions?
What's the difference between 2 line equals and 3 line equals?
The 2-line equals usually means equals in the normal sense of the word. And then the 3-line equals is more often used for any kind of equivalence relation. Not always. What's that?
Is there a 4 line?
I have not seen one, but if you come across one in use, maybe that'll be interesting.
Or you be a pioneer and make one up.
There it is. Look, I'm doing it right now.
Super. Sorry, you lost your shot because you haven't.
Oh man, thanks for the idea. I'm gonna be famous.
There's a 5-line A.
Yeah. See. Okay.
Stop talking. Patent pending.
Questions? Okay. So we got through equivalence relations. I think I'll stop there and do partial orderings in class on Thursday, the partial orderings and total orderings. As you get started on the assignment, hopefully maybe you've looked at it already, but if you have questions on it, reach out. On Thursday, We will spend the first part of class finishing up this section, which won't take very long, and then you'll have the rest of the class time to work on the assignment.
Great.